Welcome to part 5 of chemical kinetics. In this chapter what we're going to look at are the actual molecular collisions and the things that are going on at an atomic molecular level that actually cause these rates to occur at certain speeds. So we're going to look and see what actually creates an effective collision, the mechanisms that are involved, because it's usually multi-step, and so we're going to look at that and see how a certain step will determine the overall rate. We call that the rate determining step, usually the slow step. And then last, we're going to look and see how catalysts can affect the rate. So in order for a reaction to occur, you have got to have an effective collision. And an effective collision has got to collide with the correct energy, and it has to be oriented correctly. So it has to hit at the right spot, and it has to hit hard enough with enough energy to break bonds apart and then have enough left over to create the bonds that you're going to need in the product. And so it's just showing you, it's kind of a random thing. So, molecules are always moving around, whether they're in liquids or gases or whatever. And so if they're just sitting there at room temperature, it's kind of a random thing. And so anything we can do to increase either the energy or the orientation or statistically the likelihood of that effective collision happening is going to increase the rate. And so if I add more molecules to this, then I'm going to have more in there, then they're going to be more likely to hit each other the right way. If I add some type of energy, like heating it up, it's going to increase the energy of the system and make it more likely. So, and then last, we're going to see how catalysts actually help us orient the molecules and speed up the reaction. So when we have two molecules that are going to react, they are going to collide, and they collide with enough energy to get up to this activated spot here, and they are properly oriented. So when they hit, they're going to be able to break the bond that needs to be broken and make the bond that needs to be taken. So what we're doing is kind of this. So we're colliding here, that one's taking the other red, and then it's leaving this one. And so once that happens, then those come down and we're going to have our products here. Notice that the activation energy is the energy that it takes it to get to that activated complex, also called transition state. And then the energy released by the reaction is going to be the difference between the energy where we were when the reactant started and the energy of the products where we end. So this is the energy that's actually released by the reaction. So this one would be an exothermic reaction because we are releasing energy. So we made energy. So, and there are many more ways for it to be ineffective than there are for it to be effective. So it has to be just right. It's kind of like Goldilocks and the Three Bears. It has to be just right for it to happen. So we usually just write one chemical equation for a reaction, and we're used to doing that, and we balance that, and we see all the atoms and elements that are involved. But most reactions occur in a series of reactions, and often 1, 2, or 3 molecules are going to be involved. When you get much farther than that, it tends to not happen. It would then react, and then you'd produce a product, and then maybe the product would do something. So in just a general chemical reaction, we're going to use what's called reaction mechanisms, which instead of the reaction equation, the reaction mechanism is the step that's involved in that. So you might have 1, 2, or 3 steps for all of this to occur. You're going to break bonds, then they're going to find each other and make another bond, and then produce that product. Okay, and so if you know the rate laws for the mechanism, okay, and each step in that we're going to call the elementary steps. Okay, if we know what the energy is in each of those steps, then we can figure out what the net energy is going to be for the overall reaction. So when I have hydrogen gas reacting with iodine chloride, we produce hydrochloric acid and iodine gas. And so that happens in two steps. The hydrogen gas reacts with the ICl, notice 1 of the moles of ICl, to form hydrochloric acid and hydrogen iodide, okay? Hydrogen iodide because it's a gas. Then the hydrogen iodide, which is the product of the first elementary step, is going to combine with the second mole of the ICl, produce more HCl, so we get 2 moles of it, and I2. Notice nowhere in the overall reaction do you see hydrogen iodide, because hydrogen iodide is that transition state or that activated complex. So it is used up in the second step of this reaction. And so that book is showing you that. Okay, so since it's consumed, we don't put it in the overall reaction because it really isn't important. And so here's another word for it, is an intermediate. Okay, so that's something that you use, that you produce in a step, and then you use it up before you get done with the entire reaction. So you can call that an intermediate. So these involve a concept called molecularity. And molecularity is basically how many particles there are in an elementary step. Okay, so if you have 1 particle, then it's a unimolecular step. If you have 2, it's bimolecular. If it's 3 or more, it's termolecular. Okay, you don't see a lot of termolecular steps. Usually you're only going to see 2 steps, especially in general chemistry. When you get into organic, you have some crazy stuff. That's a tease for when you get to go to organic if you're going there. All right, so rate laws for elementary steps are basically done the same way that we did the rate laws for everything else. But the overall rate laws, must be determined experimentally, but the rate law of an elementary step can be deduced from the equation of the step. Dun, dun, dun. Okay, so if you're taking H2 and ICl in the first step, okay, the rate of that first step is going to be the concentration of each of those. And the rate of K2 will be the HI and the ICl, because these are elementary steps, okay? It's not an overall equation. And so the reason I know that is because of molecularity, okay? If I have 1 reactant, A, then the rate will be K times the concentration of A. If I have 2 A's, it's going to be, or A plus A, then it's going to be A squared because it's a molecularity of 2. If it's A plus B, it's going to be the rate of A times B. Okay, and this really is the same as this one, because really what you're saying is K times A, right? Because you had A plus A. All right, and then if you have 3, which is rare, we said it's going to be A cubed, etc., etc. So mainly we're going to be looking at these 3, and so these 3 you should be able to kind of remember, and you'd be able, by the molecularity, you have 1, so it's going to be K times A. You have 2, so it's going to be K times A squared. Or you have 2 which are different, it's going to be K times A times B. Okay? And that's just because we know that because of the molecularity of elementary steps. So in most reactions, you're going to have what we call a fast step and a slow step. And the rate determining step, that is what determines how long it's going to take it, is going to be the one that occurs slower. So when you do something, a lot of times it takes you a little while to produce like that intermediate product, and then once you produce it, it used up really fast. So your production of, like when we were talking about HI and the one before, might be slow, but once you produce it, the HI adding to the other reactant producing the other products may be very quick. And so the slow one would be the one that determines the rate. And they're giving you in the book an example of how if you have, like, y'all are all in 3 lanes coming down here, and I don't know why, but usually people in Mustangs or, Chargers or something are these guys, right? They're not going to get over until the very last minute. But what happens is that I've been going along like I'm supposed to in this lane, at a regular speed. These guys wait till the last minute, so they cause kind of a traffic jam and a bottleneck, you might hear it called. So that slows all these other people down, so that's why we end up sitting in traffic. So these guys over here are our rate determining steps. So if you look at it in terms of a mechanism, we've got 2 steps, we said, in this proposed mechanism, okay? So I've got NO2 plus CO gives me NO and CO2. The observed rate, that is, I did an experiment and I found it to be the overall rate expression is K times NO2 squared. So my proposed mechanism based on molecularity, right, I got 2 of the same thing here. So the rate's K times NO2 squared. And then I've got NO3 and CO, and that's 2 things. So they're going to be multiplied by each other, and so they're going to come next. Now, in this one, the first step is the slow step. Now, I don't just know that because I know all about NO2 and NO2 doing their thing. That's because when I look at the energy diagram, okay, I can look down here and I can say, okay, I have in the first step, so you're going to see 2 peaks on this, okay, 2 humps. The first one is going to be that first reaction where you got NO2 plus CO. All right, and so it's got quite a bit of energy to overcome in order to get up here and form that intermediate. Okay, it's forming the NO3 and NO. Then it's going to react, and then the second reaction is going to come in, and notice the energy of activation is super small. Okay, so the EA2 is really small, so that means that's going to be a lot faster than this one because it's not very much energy has to be overcome in order for that to happen. And then once that happens, it's going to go down and form my products. So step 1 has a higher activation energy, a smaller rate constant because of that, and it determines the overall reaction because it's the rate determining step because it's slow. So see how that works? So you can look at an energy diagram and you can tell which one is going to be the rate determining or which one is going to limit how fast you can do this. And so when you're in industry, you're going to try to figure out ways to make this go faster, okay? Because this is your slow step. So this is where you're going to try to figure out a catalyst or something like that to increase the speed of this reaction and lower that energy of activation. So we use catalysts in industry a lot because we can put them in there, we can reuse them, okay, because they will affect the rate of the reaction without being used up. Now, eventually they probably will be used up, but they're nice because they sort of regenerate themselves after they're used. And most of them speed up the reaction, and we call those a positive catalyst because it speeds it up. So if you need, and sometimes you need to slow down a reaction. If something's explosive, that's a fast reaction, okay? So you might be able to put a catalyst in there that would slow that down so it wouldn't be such a vigorous reaction so that you could contain that reaction, get your transition state, and then move on to the safer part of that. But a lot of times when we think of catalysts, we're thinking of speeding up. And so that's what this example is over here on your energy diagram. The amount of activation energy, okay, goes from where you started up here, okay? That's without the catalyst. When you add the catalyst, though, notice it's a lot less, okay? Even when you add these two together, that's a whole lot less than that total. You see two peaks sometimes with a catalyst because the catalyst binds to one of the molecules and then it releases, so that's what you're seeing there. But notice how it's decreased the energy of activation by using the catalyst, and that's how they work. Now, specifically, how do they work? Well, you can have a couple of kinds of catalysts. You can have a homogeneous catalyst or a heterogeneous catalyst. You probably remember those terms from last semester. Homogeneous means same, so that means all of your species are in the same phase as your catalyst. A heterogeneous means that your species is in a different phase from your catalyst. So in a homogeneous catalyst, everything would be in a gas, okay? In a heterogeneous, you might have a solid and a gas, okay? So they would be different. So if you look at a homogeneous catalyst, all right, they're all in the same phase, and so they're all, getting together and bumping into each other, and they're assisting with this and making it more likely for this product to be made. In a heterogeneous, and these are the ones we think about, so this, if you've ever heard of a catalytic converter, that's like in your car, right? Okay, a catalytic converter, you have a solid catalyst that's in there, and then you have the exhaust that's coming in, and that converter will take some of, it causes a reaction to occur so that you're not going to emit carbon dioxide, okay? And so this is actually allowing the molecules to get close enough to where they're more likely to interact with each other. So they kind of bump down here and stick, and another one sticks, they react, and then the product leaves. So that's how catalysts work. And that's why they don't really change. They might change their form while it's happening, but then they can change right back into what they were and be ready for the next molecule. So they give them a different path to follow. They put them closer together or whatever, and so by doing that, it requires less energy for them to have to randomly meet, okay? So the heterogeneous, as I said, hold a molecule in proper orientation for the reaction to occur when it has a collision. Now the homogeneous catalysts actually react with one of the reactants, form an activated complex that's stable, and then react with the other atom. And so, like I said, either way, they're binding to something and orienting that exactly right, so it increases the likelihood that it's going to have an effective collision. And so, as we saw in the earlier one, this is just a little cleaner picture of it. When the activation energy lowers, that means that it took less energy for the reaction to take place. And if you lower the energy, notice that if you had to reverse that, it would be a whole lot less energy to have to reverse that than you had it before it was catalyzed. It pretty much, you couldn't reverse it. It would take too much energy, right? I mean, to feasibly do it. You could do it, but it wouldn't make any sense. So your change in energy overall of the reaction is the same, but the energy required for the reaction to occur is going to be much lower in the catalyzed version. All right, that's the end of part 5 of this, and that's the end of chapter 14, our chemical kinetics. So make sure that you do your homework online and you work your practice problems. I've worked examples and I gave you practice problems to work. If you want extra problems, let me know. I'll try to fish some out for you, but I think you got plenty to do, especially as fast as we have to do it. So get this done as quickly as you can. Make sure you take your practice test after you've finished everything else, and then your practice test should help prepare you for the exam. Just don't forget that you have concept questions. That's why I have that fill in the blank on the in-class notes, so that you can fill in the blank as you go, and that'll help you pay attention and remember that you have concepts. Some people like to do flashcards or Quizlet or something like that for the concept things, because you will be required not only to know the definition of them, but to be able to apply the concept. Okay, so in chemistry, it's a higher level of learning than just being able to regurgitate information back. You have to take that information, understand it, and then use it.